Cool. I thought what's interesting to talk about is Swift, actually, because it won't be familiar for most people. And what's the purpose of using Swift to write embedded programs? What's the benefit of it? And what's interesting about it? And then towards the end of the talk, I will try and do a demo. And then we can start talking about my journey and how I actually created it, if people are interested in that in the Q&A section. We've started a little bit late, so we'll see how we go. So first thing, I'd start off with a little about me. I've been programming since, well, I mean, since I was little. I started on BBC Micro, BBC Basic 6502 assembler when I was a weean, and then started professionally with Fortran 77 in 1993, and then moved into PL SQL, enterprise stuff, Delphi, Java. Finally ended up in banking in C#, the whole .NET world. And then about 10 years ago, well, it's a little over 10 years ago, I got interested in iPhone programming. And 10 years ago, I went professionally into iPhone programming and Objective-C, that kind of thing. The reason I'm talking about this is to sort of give you an idea of some of the languages that I've done. I'm not sort of completely fresh, you know, so the first thing that comes into my eyes is, oh, wow, this is amazing. This is that's out there. I think lots of different languages, I'm sure a lot of you will agree who are programmers or have dabbled in it, that different languages have different strengths and different weaknesses. And there is always this sort of thing, oh, the new language is coming along that's going to fix everything. And then, you know, you've been doing it for a while and you think, oh, okay, well, actually, we're doing the same thing we've done before. And actually, these guys haven't invented, they haven't got a very good error parser, and it takes them a year or two to get their error parser up and running. And then, you know, oh, we've invented this thing called a function. We've invented object orientation. You're like, well, I've been here before. So I wanted to talk about what's sort of different and interesting about Swift. Now, Swift came out, so it was probably started about 10 years ago by Chris Lattner, who was the guy who invented LLVM, which is a compiler infrastructure, which is sort of quite widely respected, and Clang, which is probably one of the other main C compiler, the other main open source C compiler that people know. So there are loads of C compilers. Obviously, there's all different. Anytime you make a chip, someone invents a C compiler. Intel had their own, you know, all these different ones. I'm sure IBM have had 2 or 3. Clang is using the LLVM backend, and it's a well-respected compiler. It's used in lots of things, and it's very, very widely cross-platform. Apple had obviously created Objective-C some long time ago, I think late 80s, early 90s, and they used this in OS X, and then they brought it over to iOS, and they obviously started to improve it and added features to it. But fundamentally, they decided at some point that they're going to invent a new language, which seems a bit nuts. But and when I first saw it, I must admit, when people told me about Swift, so out of the blue, 2004, they're doing all the usual stuff. Here's the new iPhone, it's this, this, and this. We've invented this new language called Swift, and I was not impressed at all, because I'm like, oh, here we go. This is just Apple doing Apple's thing, where they've got, you know, oh, I've got to invent our own language, and now you've all got to drink the Kool-Aid and have our new language. And so I was a bit like, okay, fine. But then they were saying it's very fast, it's statically, it's strong typed, it's statically compiled, all these sorts of things. And I was just thinking, I don't see how it's going to be better than Objective-C, but they were really strongly saying it's going to be faster and better than Objective-C, and the syntax is great. And I thought this was all about getting rid of those strange square brackets that you have in Objective-C, which are a remnant of its Smalltalk roots. But actually, it really is quite different. And as I started to use it, I started to understand and grok, if you like, what the point of it is. And I think the fundamental point is about it's about predictability. It's about leaving you as a programmer with very little doubt between you and the compiler as to what you mean. And we sort of get into why that's important. And it's actually interesting that I've had experience of all of these languages, and I've gone through all of these problems in the past, and I've had all of these various issues with it. And I suddenly thought, oh yeah, now I can see why this is a good idea. I can see why that's a good idea. So that's why I wanted to sort of touch on that and talk about some of these things. In order to give background on it, the thing I'm going to have to talk about, or have I covered all of those? Yes. Objective-C, Swift, other, because I've done, I don't know, I lost count, 30 or 40 different scripts and languages and God knows what. In order to talk about this, the important point is talking about microcontrollers. Now, I said this for embedded, so Swift for embedded was the title of my talk. That said, I'm really going to talk about microcontrollers because I think they're interesting. I think they're fundamentally, it took me a while to understand this as well when I started to get into microcontrollers. They're fundamentally different from the sort of programming that most of us programmers have done on other systems. And I just wanted to give a brief overview. A lot of this, people like Ben's going to know inside out, but for people that don't know microcontrollers and perhaps more on the hardware side or who are more Raspberry Pi people, what is a microcontroller? What's the point of it and what's special about it? So it's a very small, self-contained, simple computer in inverted commas. So it's got a program, normally stored in flash memory, some working RAM, often not very much, a CPU, of course, with all of the parts that, sort of arithmetic, possibly floating point operations, peripherals. So things like SPI, I2C, often very simple things like that, serial UARTs, things like that. Sometimes more advanced stuff can bus things if it's going to go in a car, and various other bits and bobs like that, but it's all self-contained, all in a tiny little piece. These things, as I understand it, started to become a thing in, to some extent, the 80s, but particularly in the 1990s, where you started to move all of these things onto one chip. And of course, a lot of us know about things like SoC, system on chips, because these are being made famous by things like an iPhone, but they're popular all over the place. So it's got an SoC, it's got some of the things brought into it. A microcontroller really is pretty much a standalone device. So you can more or less run a microcontroller with just a power line, and it's got a programmable computer in there that can run a simple program. And they're also amazingly cheap, which is actually very important, as I'll talk about in a minute. This means you've got something like a computer for $1 or less. So the price of a 555 timer or various other discrete components, you've got a whole little working system. And this is, we'll sort of get into that again. I'm going to go through these points a little bit. This is the point of it in a way, because it's so cheap, because it's self-contained, you can use this, as I think Ben said in one of his previous talks, instead of discrete electronics. So you can say, rather than writing the whole timer circuit or all of these oscillators, flip-flops and so on, I'll just write a simple program in here, throw in this part that costs 30 cents, and it's done. And that gives some options that just haven't been available in the past. Bare metal programming is a feature, not a bug. Now, what I mean by that is, at first, when you come to it, it can seem disorienting. So most people, like I did, come to the Arduino IDE, just the normal thing that people go for at first, and they see the setup function and then the loop function, and they go, all right, fine. They copy various examples, but they don't understand that you're not running a program inside an operating system the way that most of us normally expect. So you don't have error handling that'll take care of things if it crashes. You don't have process isolation. The memory is all yours, all the hardware is yours. Anything you do is up to you what you do with that. And that's at first daunting for someone who's come from another background, because you think, oh, well, every time I make a mistake, then it just goes wrong and I have no idea why. It just goes into a tight loop, or, it behaves erratically and I don't really understand why. But it's actually, once you get past that into the way of thinking of you've got control and you're responsible for it, this gives you the power to turn something on and off at exactly the right time and to just control the hardware completely. And that's what's important. It's not that it's fast, it's that it's deterministic. So that you can say, when you write a program, you know exactly how long something will take, because it'll take this many cycles. And then you can flip a pin up, and then you know exactly how many cycles before you flip the pin back down again. And that way you can do things like bit banging, creating a waveform, which is what I'm going to show in my demo. And it's something that you just can't do reliably on a full-size operating system, because they don't have that real-time aspect. They don't have defined guarantees as to when something's going to run. So what I say when you're dealing with this is, get threading, containers, processes, all these lovely things that people like to talk about if you're on a Raspberry Pi. So I'm going to use Docker. Don't need Docker. It doesn't happen anymore. You don't have processes, you don't have containers, you don't have threads. You do one thing perfectly. So you run one simple program perfectly. These are super low cost and super low current usage. So, 20 milliamps when I'm running it just on a bare breadboard, you can run it a lot less than that. And because that's the case, because they're so cheap and because they're low power, that changes everything. If you've got 5 things that you need to do, instead of running 5 processes on your Raspberry Pi, you get 5 microcontrollers and get them. One of them is going to be listening to the keyboard, one of them's going to be flashing an LED at a certain speed, one of them's going to be controlling a motor, those kinds of things. And it can still run on a battery for a year. As a result of all of these things, these microcontrollers are everywhere. You didn't even know it. They're in all the devices around you. Your washing machine, of course, will have one, but various other things around you that you wouldn't even have thought of, toys, etc., will have microcontrollers in them because it's just this efficient way to do things. And as a result, it's actually a very interesting type of programming that most people don't have access to. And I'll start to go into why was that. So one thing I'm also going to talk about briefly, because I've chatted on a bit, is MicroPython and various other things like that. I'm not singling out MicroPython, okay? There are lots of other approaches, Pick Basics, Scratch for Arduino, various other things like that. And these address the fundamental problem. These address the problem that basically developers like me come to the platform and get overfaced by C and C++ and just like, oh, I can't face this. So people are just put off by this and they don't go near microcontrollers. So in order to deal with that, people like Adafruit have created things like MicroPython. But the thing is, the microcontroller code must be fast, efficient, and above all, predictable in production. Otherwise, you will get strange errors and strange bugs that just don't work in a hardware environment. All high-level languages, even C, create abstractions over hardware and assembly language that many programmers would rather ignore. But actually, there is a different level of abstraction. So the kind of abstractions that you get in C still leave a degree of predictability. I put Starnix here, as in Unix, BSD, Mac OS, and controversially Windows, which is kind of a Unix. Almost all knowledge of the underlying platform is taken away, and that's essential for your productivity. And the abstractions add security and flexibility. In bare metal programming, it's not that. The microcontroller's bare metal is always there, even if you've got RTOS, taking away some of the things, taking away bare metal prevents many of the most important types of microcontroller programming from working. And finally, it's impossible to fix security, I would say, on those things. So you're telling me C is the one true language? Spoiler alert, no. Arduino code is actually C++ anyway. C++ is a super powerful language with endless ways to subtly trip yourself up: generics, pointers, classes, structs, RTTI, myriad different compilers and standards, and the compiler wars. Even C itself is not as simple and safe as people like to believe. Undefined behavior is much worse than you think, and much worse than normal bugs. One example is the famous buffer overrun, where you don't take account of something and you get a buffer overrun and memory goes all over the place. Maybe a hacker that's taking charge of it. It may just be, as I had in one case, I had a 1 byte buffer overrun of one of my earlier programs when I was first writing C, and the program was controlling a dimmer switch in the corner of the room, and occasionally, about once every few hours, it would just flicker and disintegrate and just go crazy, because I was moving along 1 byte at a time, and each time it received a network packet, it was moving along 1 byte through memory until it hit something important. So this sort of undefined behavior, or loosely defined behavior, which is kind of almost a signature of C, and it's, well, it's defined in this compiler and not that compiler, and so on and so forth, is so damaging, because it creates these bugs that you just don't pick up in time, and they always come out in production, and frequently they're creating security weaknesses. An expert will say, yes, but I know my compiler inside out, and if I really want to be strict on it, then I'll use assembly language. Yes and no. That is kind of true if you never stretch, but then the minute someone comes along with a new chip, you could be on the back foot. Plus a new compiler version comes out, you could be on the back foot again. And I think there's almost a culture in C of, well, this is just how it is, you can just have to deal with it. And there's something about C having been around for so long and being so widely used that it's just expected that will happen. I think I've covered all of those sorts of things. So for example, null pointers and invalid pointers are going to have to speed up a little bit. Newest languages recognize some of the costliest and hardest to fix mistakes of the last 60 years. One person, I think, estimated that null pointers and invalid pointers was something that should never have been allowed to happen. They should have basically just designed languages so it was impossible, and consider this to be a multi-trillion-dollar mistake. Swift, and to some extent Rust, always preferred defined behavior. What will happen in that integer conversion? You must be clear between you and the compiler. It will force you to be clear on those things. Where is that variable first initialized to a value? Code that accesses undefined values will not compile. Null or invalid pointers, no such thing. So defined initialization. This isn't getting into the Swift stuff now, so it's slightly less abstract. So I've got a Swift program here. Now, obviously, you don't know Swift if you've not done it before, but I think you should be able to read what I'm doing here in this first program. So I've got a variable that's unsigned integer 16. If a specific pin is set, then I'll read the temperature from analog pin A0. And then after that, I'm going to write it out on the I2C bus. So something fairly straightforward. This won't compile because I haven't defined what the value of temp is under all circumstances. I need to define what the else is on that, and I need to set temp. Otherwise, it won't compile. Basically, Swift will not allow you to leave things undefined like that. Higher level data structures. So let's create a simple struct here. It's got a temp, a time read, ambient data if you want to put that in. Here's an initializer where you pass in the new temperature and new time. Will not compile because you haven't defined what's happening with all of the members. So you can't create an initial struct unless you define what goes into every single one of the members. Now, how is that possible? Of course, you say, because sometimes you're going to need loops. One thing's going to depend on another. Sometimes you don't know the data beforehand. So the programmer must always define the edge cases. In order to be able to do that, we have this funny little syntax. If you look at ambient data, user notes query of a thing called an optional. And we'll get into what that actually is or isn't at the end of it. So now this will compile. And what does that mean? Well, actually, there's a special value that you can put into optionals called nil. Now, I can imagine what some of you are thinking, but I'll get into what it really is in a minute. So the previous thing here actually just defaults ambient data to nil. So now every member is defined in the struct and that initializer compiles. And you can use it even though you don't pass ambient data in that initializer. What optional actually is what's called a discriminated union. So in fact, it's an enumeration. It can have two values. So optional is something with a generic parameter, user notes, something like that. And it can either have a value of none or some, but this isn't a nil pointer. Even if you have a class in there, this is not a nil pointer. It's something syntactically distinct. It's a variable that can have one of two things. And if it has some in it, then you can add extra data in there as a blob, which also has to be defined fully. So nil is just an equivalent to none as one of the possible options. If we're using it, as a result of that, you have to define what's going to happen. So we've got the temperature. I've cleaned out the initializer from before, just so we don't run over on the slide. It's not too big. So we've got some function here that's returning last temperature data. We send it to the I2C bus, but I haven't defined what's going to happen if ambient data is nil. And this function send to I2C bus is one that requires ambient data to be passed. It's one that does something with it. In order to handle that, you have to explicitly say, if ambient data is populated, if let ambient data equals last data to ambient data, then send to I2C bus. Oh, have I got these the wrong way around? Yes, I've got these the wrong way around. the line should down there should be above, and the send to I2C bus should be in the second else clause, because that's basically the case when you don't have ambient data. So actually this wouldn't compile, just shows that I wrote this slide by hand rather than putting it into compiler, which would have told me no. But you can see how it works basically. And this is, once I got the idea of this, I realized what a powerful syntax it is and why it's actually a really much better language than C, C++, Objective-C that I was using beforehand, which is why I've been very comfortable with writing Swift code for, gosh, 7 years now, and now making my own compiler and my own products that actually uses Swift code underneath the hood. Integer conversions. Now, this is where it gets a bit abstract, but if you guys have written C programs, then some of this may be familiar with you. for you or not. So this one here, temperature analog read pin A0, because analogs, the ADC on an Arduino Uno actually returns a 10-bit value. That in our product goes into an unsigned integer 16 variable. When I write this next line out, this is just sending a single byte down the line. Sorry, this one is sending the full double byte value down the line. The third line there, send SPI slow, is just sending 1 byte to your SPI peripheral, whatever that is. Will not compile because the two types of integers are incompatible. Now, if you're doing that in C, you might get a warning, or it might just truncate it in some way because it says, you're the programmer, you know what you're doing, fine, turn this uint 16 into a uint 8, and I'll save you time so that you don't have to write down explicitly what you want to do with it. Unfortunately, that lax attitude, it's one of the things that causes 90% of the bugs in C. And a C programmer will avidly defend it and say, no, you need to have that because I know what I'm saying and it's expressive. Otherwise, I've got to write all this guff around it. But actually, it's just not worth it for the value that you get out of that brevity, for the number of bugs that it introduces. It's actually better to have a much more explicit syntax, which is what Swift forces you to do. So here, you have to specify that you're going to truncate the temperature down to an unsigned int 8, which will probably chop off the last 8 bits of it, which might well be what you want to do, and it might not be. But you'll have a much better idea as a programmer that you're explicitly doing that. And then, most importantly, the compiler will know exactly what to do underneath the hood. It won't depend on which compiler you're using. It won't depend on various different circumstances or the byte alignment or what processor you're on. It's absolutely explicit what you're doing. Likewise, signed to unsigned integer conversions must be explicit. This is a small looking change, but with big consequences. This removes whole classes of undefined or unexpected behavior. And most strange of all, if you come from C, integer arithmetic between two different types of integer is forbidden. So you have to cast the same type of integers. This means you can't add a uint 8 onto a uint 16. And most importantly, it won't do that thing in C where it says, oh, all right, you're adding these two numbers together. I'll guess the type that it's going to do, and then often truncate it to 0, which is what's happened to me on a few occasions and caused me to spend, well, quite a long time trying to fix some of these things. Okay, I'm going to stop screen sharing for a minute because I want to switch to my other camera. So let's do this. All right, now I think video-wise, you guys are seeing me, right? Let's switch to our traffic camera down here. Can you all see my scope?
Yep.
Now, what I'm going to try and do, because we're short on time, I'm not going to do an actual live coding demo. I'm going to show this the kit here, then I'm going to show the program, and then I'm going to show the program uploaded onto the kit, so you'll see the net result of it. Because I think anything else is just going to be a little bit too long-winded, and I'm going to drop out the last few slides here, I think, because otherwise actually I could do 1 or 2 of them. Okay. Right, let's bring up the program. So the kit, very simple to explain. This is an Arduino Uno underneath. This thing on top of it though it looks very dramatic, all it really is a shield that's got various different things, buttons and LEDs and so on and so forth on it, called a mini danger shield. And the only thing that I'm using it for is 2 LEDs here, which are on pins 5 and 6 of the Arduino Uno underneath. That's the ground. And then these are both being read into the oscilloscope. So the purpose of this is I just wanted a couple of, I could have done without this actually, I could have just shown you what the results are on the oscilloscope, but it's always nice to have some LEDs, and I couldn't be bothered to get a breadboard out and loads of wires all over the place. So I just banged this danger shield on top. I will now pull up the program. So I can do a quick screen share again. Let's do this. Okay, can you see the program now?
Yes.
Right, I'll pull this over. So that's fine. So I'll take you through the program as quickly as I can. This was going to be a fun thing to write, but we're a little bit tight on time. Plus also I've been chatting too long. The syntax should be fairly straightforward for most people. So if ask questions if anyone's confused by it, but it shouldn't be too alien if you've written Arduino programs in the past. It's not C, but it's not massively different. First thing we're doing here is defining a couple of constants. In Swift, you define something as let, you can't change it further down. If you define it as var, you can. So it's sort of a little bit like JavaScript, but much tighter. This is one thing that I'm not quite sure whether I basically needed it in order to make this thing function accurately. It's turning off the timer that normally runs ticks in the background, which would slightly throw off my bit banging. Now we're getting into the more interesting stuff. So the first thing I'm going to do is set the 2 pins 5 and 6 to be output mode. One of them I've named LED and one of them I've named trigger pin. These aren't fantastic names. Now we're getting into the functions, which is where the interesting stuff is. So I'll show you the main program down here. We'll have a quick look at the functions. Here's one of the functions. First thing it does is write the trigger pin high, wait for 100 microseconds, then write the trigger pin low and wait for another 100 microseconds. So when I call that trigger function, you can imagine what it's going to do. Well, before we look at these two functions, we'll have the actual meat of the program. So it runs through these statements, defines these functions here. So which do things like set constants, stop the ticking, and set those 2 pins as output. Now we've got an infinite loop. First thing we do is run the trigger. This really is just because I couldn't get the demo to work properly without this trigger on there. And then I call function S, function O, function S again, and I wait 5 milliseconds. Function S writes the LED pin high, waits 100 microseconds, writes the LED, waits 300 microseconds, high, high, high. So it's writing the LED pin high 3 times. This one's doing the same thing, but with a longer high segment with the same length low segments. What I'm doing here is this slightly whimsical idea. I thought I'd make it output SOS to do it super, super fast. You could actually make it go faster than this, but let's not push the demo gods too far today. So this is going to send an SOS signal, hopefully, down the pin, and we'll see it on the oscilloscope, an SOS signal. Now let's give it a chance to upload and see what happens. Okay, now I'll flip back to the camera, so I have to stop sharing with me. Just press this. And now we can see on the scope. Can you guys trace on the scope?
Yep. Yes,
So what I want to do, so the reason that I put in, I beg your pardon? The reason I put in this trigger pin was in order to get the trigger stable. So basically all it's doing is firing off 1 pulse on channel 2, which is starting the sequence, because I have a bit of a cheap oscilloscope, so I couldn't get it to work much better than that. I needed this kind of trigger voltage to make it work. And what I wanted to do is I'm going to try and zoom in, and hopefully it'll remain stable on here as I zoom in. I'll go in, can I pull in one more? Let's try that. It might destabilize the waveform if I do that. It's actually not the waveform that's unstable, it's my oscilloscope. So if we have a quick look, oops, let's bring that down, wrong control. I did practice this, guys. It's just doing live oscilloscope work is a bit of an interesting one. So here you can see the trigger pulse, which is 100 microseconds. Then you've got about 100 microseconds wait, another 100 microseconds, 300 microseconds wait, another 100 microseconds. You can see there is a small delay here where the program's running and turning something on and off. You could allow for that if you needed to get it exactly right. The thing that I wanted to show is if you see how stable that waveform is, and this is quite a fast, this is operating pretty fast. So this whole, let's see if I can bring it in so you can see the whole waveform. It's not quite the right size. That's dit, 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 da, 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 dit, dit, dit. And that's 4 milliseconds overall, and it's stable. And I wanted to point that out because the point of it is that the program is running stably. If you did that with a toy program, your MicroPython or something like that, then I don't think you'd get a stable program like that. That's what I'm trying to show. I think that's probably enough for that demo for now. Let's switch back to me. Dual camera setup, pretty ambitious. And I'll go back and finish off the talk, and we can go into very quick Q&A if there's time. So let's share screen. Q&A. Okay, does that look okay?
Yeah, looks fine.
Okay, we'll go really quickly over these ones. MicroSwift, which is the language that we're using here, is the sort of trade name that we've come up with, this variant of Swift. So we've taken Swift. It was in some ways still a bit too big, too memory heavy, etc. for microcontrollers. So we cut out some of the parts of it, and we're slowly inserting some of those parts back when we can be sure that they operate at the right speed and they give stable performance. So it's been customized, the embedded environment. Things like arrays are really quite different, but otherwise it's very similar to Swift 5.3. Formal launch was only last year. Many promising new routes for the future. See Martin's university thesis for a good unbiased summary. Shameless plug, I will keep this quick. Our IDE is now 4 years old and stable, having reached 4.5, paid but with a free trial and very reasonable pricing. Coming soon, free for universities or pay with no risk equity for startups. Talk to me if you want to, demo codes, that sort of thing. You never know, I might be able to pass you something. And looking for investment, if anyone knows investors or can put me that direction to develop the Windows and Linux versions, ARM ESP32 and RISC-V versions. Apple, the elephant in the room. I don't think we're going to talk about that. We can go into that for Q&As. And thank you very much.
Thank you.
Thank you, Carl.
Anyone have questions?
I'd like to ask, what do you consider the advantages compared to, say, TinyGo?
TinyGo is an interesting one. I think TinyGo is, so disclaimer, I haven't used many of these other ones. I know the creator of TinyGo, Ike. His view on it is for something like an Arduino, you just haven't got enough beef on it because it's a garbage collected language. So he said that he's generally, it does work on there. I think generally garbage collection, to me, philosophically feels risky on a microcontroller. I'd be interested to see if you ran something like this on TinyGo, what the comparison would be. But yeah, TinyGo is Rust, AVR, Rust, Swift, and TinyGo are all pretty solid things. I think they're all interesting stuff. So wouldn't discount it. Definitely worth a look. TinyGo. I've backed Swift. That's the horse I've backed, and I think it's probably the right one. But we'd be interested to see. It is funny that Aki actually said he doesn't consider TinyGo is really very valid on that platform. So then maybe he's changed his mind since then.
So have there been any studies done on I don't know, actually bugs that make it into production with Swift compared to these other languages and things like that? There must be something.
I don't know. That's a really good question, actually.
Quantitatively.
Yeah, I don't know. Yeah, that's a question.
What's the question?
Whether there's any university studies on it. Whether there's been any studies done on the percentage of bugs or the kind of frequency of bugs that make it into production using things like C++ compared to Swift. Because at the moment you'd have to compare those two because MicroSwift is so new that very few people are using it, I'm afraid.
Yeah, I mean, the thing I like about Python is it's got such a great community. It's so easy to find answers for things.
Absolutely, yeah.
One of the things
which is why I can see why Adafruit went with the MicroPython. I mean, I can see because for someone who just wants to blink a light or turn something on and off, why not?
The thing that drives me crazy about Python is, I guess that, just variables just being passed around with different types and all that sort of stuff.
Yeah.
So many times, it's the Python's using what I think is a number as a string, and it just ends up being a nightmare. Track down what the problem is. I know it's coming up with ways of dealing with that, so you can typecast it. But Sure,
Yeah, I think it's
a lot
going to be one of
people
these
have
things
problems
like
with Python.
JavaScript, where people eventually just decide that strong typing was what they should have done in the first place.
Yeah, strong typing can really save you. I can definitely get behind that.
It's the same thing again. It's where do your bugs occur? Like, when the world's going to tell you that you've coded it wrong, is it going to tell you during compilation, or is it going to tell you when the linker runs, or is it going to tell you in runtime, or when a customer tells you? You really want it as early as possible, because if in fact, it's better if it happens even before it compiles. If you have like inline on the fly compilation that you get in a lot of IDEs these days, where it's like telling you that you typed in an invalid variable. No. I've got a question from Murray. Thanks, Carl. You flashed over the Apple side there at the end. Have you done any similar Swift work for microcontrollers? They haven't, no. I've spoken to Apple a few times. I went out to WWDC in 2018, showed the Apple engineers there. They were mixed. Some of them were very impressed and loved it. Some of them were just surprised. But they're all very positive. They've got a positive community, and they're supportive. They're not doing anything like that themselves. They sort of encourage me, but in a kind of a discreet nod type of way, I would say.
So are you the first one then who's actually tried this for microcontrollers? Yeah. Oh,
yeah.
Awesome.
Yeah. There's no other Swift on microcontrollers. There is one guy who's done a sort of Swift on a specific type of kind of heavy end ARM Cortex processor. Swift IO, I'm going to say, something like that. But it's not the same approach as me, where I'm actually saying I'm going to make a version of Swift that works on like 8-bit microcontrollers like AVR, and is intended to go all the way through. So I'm trying to create a Cortex M0 version at the moment. But the AVR version, Swift for Arduino, works in Swift for Arduino Uno. That's the kind of core product right now. Nikolai, does the toolchain support other microcontrollers like ESP or NRF? No. So I've focused on AVR microcontrollers, and really mostly the Atmega 328P, which is the one inside the Arduino Uno and various other things like that. I got it working on the Leonardo, which is a 32U4, I think. And it's sort of, the hardware support is kind of an issue, because you've got like all of the different timer registers and so on and so forth. So we're still sort of working on making the support good. The support's really good on the 328P on the Arduino Uno. You've got all of the hardware supported really well. On some of the other AVR chips, there's still work to do on hardware support. For ESP, there's no support for that. It's a completely different architecture. If I get funding, that's one of the things I want to build. That's why I was mentioning it on the slide. Obviously, I don't want to bang on about that in a meeting like this. It's unkind. Getting funding is so boring as well. What other things? So NRF, that's an ARM-based chip. I'm currently trying to get the 807021 chips. So I'm doing a version of it for ARM chips for ARM. The NRF ones, I'm probably going to try and do a port of that works on the NRF Cortex M0 based chips, if that answers your question. I see IDE costs $40. Most other IDEs are free. How are you going to compete? Fair question. I don't think it's true that all IDEs are free. I think that the free IDEs are quite popular for obvious reasons. A lot of good IDEs do actually cost money. And really, I think I'll leave it up to people whether they want to spend $40 in order to have an easier life, something out of the box, just plug it in and go, with all the work that I've done and with the other volunteers and the work that I'll be putting in with the new team. It is the only Swift on Arduino Uno, so there is that. When I go into the ARM space, it'll be a little bit more interesting. Be interesting if I do a Raspberry Pi version, because you can definitely download all those tools for free. Will people pay for an IDE then? I don't know. We'll see. Thanks, Gary. I appreciate that. Yeah, Keith said the same sort of thing. He's worked. He's a fantastic guy. So TinyGo is a great product, and Ike's a really And he's helped a lot with, even with Swift for Arduino, because he helps in the AVR Rust team that Dylan founded, Dylan McKay. So yeah, I think it's, there is a question as to whether something can be done sort of academically if you're willing to download all the toolkits and compile them and, you know, all those sorts of things, compared to, I just want to get going and I just want to play with this hardware, I want to see what microcontrollers can do. Which I think is the sort of sweet spot I'm sitting in. Anyway, I'm banging on and the Q&A has been going on way too long. Let's go on to the next speaker, I guess.
Any last questions? No?
I was curious about how much library support is there. How much have you have to put together?
Yeah, interesting
Yes.
one. So that was, Martin was struggling with that as well. So the thing is that most libraries and demo codes out there are built for the, someone throws out something for the Arduino infrastructure. What we've done, because we don't want someone to pull in the whole Arduino, you know, bump. You can put C++ code in, you can build it in line and call it from Swift. I discourage it for various reasons. One is the whole point of Swift is to make your own competing ecosystem code. That said, obviously, for practical reasons, you downloaded, so you know, you bought a part from China, you need to get some sort of source code working on it. Not everyone wants to go to the data sheet and write their own version in Swift. So you can drop in C++ code. The thing is that they end up with all of this dependency stuff. It's the whole C and C++ problem. We've found a way out. When Martin's talk goes live, he'll talk about it a bit. Probably talk to me offline because I'm conscious that I'm running over massively.
That's really good. Thanks very much. The yeah, brought some memories back of C and
Yeah, well, that's the thing. I do like
stuff.
C, but yeah, it is just that, especially on embedded devices, I think it's even worse in some ways because it's so powerful in a way. You can do anything you want in the same way that you can with assembler, and with, you know, it just does exactly what you tell it to do, of course, which is what computers are dreadful at doing, isn't it?
Thanks very much, Carl. I know got your kids waiting for you probably.
No, I'm okay. That's all right. I'll
Thanks
run
very
and check
much.
on them in a minute.
Thank you. Really enjoyed that one.
Cool. Glad
Something a
to.
little bit different. Thanks.